Hello everyone, Mr. Tomaszek here. Today we're going to do the lab called Determination of the Ideal Gas Constant R. Let's take a look. In this experiment, you will calculate the gas constant R by collecting a known quantity of hydrogen gas and measuring the temperature, pressure, and volume of the gas collected. From the ideal gas law, PV equals nRT, you can see that it's possible to determine R if you could isolate a sample of gas for which you would know the pressure, the volume, and the temperature, and N, which is the number of moles of the gas. In this experiment, we're going to do this chemical reaction. Now, later in the course, later this year, we will talk about reactions again and review things like balancing and writing formulas and stuff like that. For now, we're just going to use this equation to produce hydrogen gas, which is that H2 at the end. We're going to do it by reacting magnesium metal with hydrochloric acid, and it would produce magnesium chloride and this hydrogen gas, which will collect, measure the volume, measure the temperature, and then determine R. First, let's do a little bit of review. In the equation, PV equals nRT, P stands for pressure. And how do we measure pressure? In the early days, we measured pressure with a mercury barometer invented by Evangelista Torricelli. It consisted of a tube of mercury being held up inside the tube by the atmospheric pressure, which was distributed throughout the liquid, holding the mercury up the column. How tall the column was, or how high the mercury was indicative of the air pressure. When the pressure went up, the height would go up a little bit. When the pressure went down, the height would go down a little bit. So on a daily basis, pressure could be measured by how high that column of mercury is. And we still use that unit, millimeters of mercury or inches of mercury, to measure pressure. Nowadays, there's lots of other ways that we can do it, using aneroid barometers like these, or in our case, a pressure sensor, such as this one, connected to a device called a LabQuest. On the sensor, there's a little hole that air can go in, and it registers the air pressure on this device, set to measured in inches of mercury. We also have a thermometer for measuring the temperature as well. The V in the equation stands for volume. All right, to measure volume, we're going to use a graduated cylinder. Normally, a graduated cylinder would be used for measuring volumes of liquids, but we're going to invert it and use it over water to collect hydrogen gas from the chemical reaction. Now, N in the equation stands for moles. It's how chemists measure the amount of substance. Now, remember that a mole is equal to 6.02 times 10 to the 23rd. In this case, it's going to be molecules. That could be anything. Molecules, atoms, apples, oranges, bananas. It doesn't really matter. It's just a large number of things. Exactly like a dozen is 12. It doesn't really matter what it is. In this case, we're using the mole. So N is moles. T in the equation stands for temperature, and we're going to measure that in Kelvin. Now remember, we're probably going to actually measure it in degrees Celsius, and then we're going to add 273 to turn it into Kelvin temperature. Remember, Kelvin does not have the degree symbol because it's an absolute scale. So T is measured in Kelvin. All right. R, of course, what we're trying to find here is the ideal gas constant, which has a value that depends on what units that you use. If we measure pressure in kPa and we measure volume in liters and we measure N in moles and T in Kelvin, then the ideal gas constant should be 8.31 kilopascal multiplied times a liter divided by a mole divided by a Kelvin. So that's the ideal gas constant using these units, and we're just going to do it in 1 unit and try to see if we can come up with that exact value experimentally. Before we get into the procedure for this experiment, let's look at the reaction. First off, we have Mg, that's magnesium. That's a metal. It looks like this. This is magnesium. We buy it in ribbon form. It's kind of like a piece of flattened out wire. And when you get it, it's some kind of grayish colored because it has an oxide layer on it. So before we do reactions with it, we like to clean it off with a little bit of sandpaper. And we'll get it down to the nice, clean, shiny magnesium metal. Now, magnesium is kind of an interesting metal because it can react with oxygen in the air in sort of a combustion reaction. It lights on fire. Later in the year, we will do an experiment where we try and do this, burn some magnesium. Let me show you what that would look like. Now, it's a little tricky to get it lit here, but once it's lit, it burns very brightly. And if you were seeing this without being on video, you'd probably see spots in your eyes. When it burns, it turns into magnesium oxide, which is kind of a white powder. Magnesium oxide. That's not the reaction we're going to do. We are going to react it with hydrochloric acid. Hydrochloric acid, which is HCl. And that looks like this. It's a strong acid, something we'll also be learning about later this year. The formula is HCl, hydrochloric acid, or hydrogen chloride. All right, what's the reaction going to look like? All right, let's put a little bit of this acid into a test tube. And then we'll put in a piece of that magnesium ribbon. And this is the actual reaction that we're going to do in the lab here, in the experiment. Let me get it so we can see it real nicely here. All right, when I drop the piece of magnesium into the hydrochloric acid, right away it starts to react. The bubbles that you see there are hydrogen gas that's being released and just comes right out of the test tube. At the bottom of the test tube is still a liquid that contains magnesium chloride, and that will just stay in the test tube there, and the hydrogen gas bubbles will just float away. So in our experiment, what we're going to do is this reaction, but we want to collect the gas so that we can measure its volume and its temperature, and then we can try to determine R. Okay, let's take a look at the procedure. Number 1, obtain a gas collection tube, in this case a 100 milliliter graduated cylinder, and a 600 milliliter beaker. Instead, we're going to use this trough of water right here. And then it says obtain a stopper and a length of copper wire. Right, the copper wire is going to hold on to the magnesium. So next we're going to measure out 1.5 centimeters. We'll just approximate right here. Here's our piece of magnesium. And what we need to do is find the mass of it. So we're going to put that on the scale. Okay, first put the paper on the scale. Hit the 0 or the tare button. And add the magnesium. We have 0.06 grams of magnesium. Okay, let's write that in our data table. Magnesium used, 0.06 grams of magnesium used. All right, next we're going to take our piece of magnesium and we're going to wrap it with this thin piece of copper wire. That's just going to sort of hold the magnesium while the reaction is happening. You'll see why here in a second, because it might float. That's then going to go inside the graduated cylinder. We're going to put the cork on so it'll be in here kind of like that, inside that. But first we need to add acid to the graduated cylinder. All right, I'm going to pour the acid. All right, that should probably be enough, maybe a little bit more. All right, that's at the bottom of the graduated cylinder. And then we need to add some acid very slowly, or add some water very slowly so that it doesn't disturb the acid at the bottom. So I'm going to do this very slowly. Acid is more dense than water, so it'll stay pretty much toward the bottom there as long as I don't stir it up too much. Looks like little chunks of something in there ain't supposed to be in there. Not a problem though. We want this to fill all the way to the very top so that it kind of just overflows. All right. So now the acid is still mostly at the bottom. If I dip this in there, it might start to react a little bit, but most of the acid's at the bottom. So then I'm going to put this on, the cork nice and tight. There will still be a hole for the water to leak out. And now we can see that the acid. Now, what we need to do is get this inverted quickly without spilling up too much of that underneath this, without letting too many air bubbles in. And as the acid starts to roll its way down, we'll start to see the reaction happening. Okay, the reaction is happening, and you can see the bubbles that are rising to the top of the inverted graduated cylinder, and we are collecting hydrogen gas. Little tiny bubbles. All right, now we're going to have to let this go for a while. So what we'll do is clamp it so that it doesn't tip over and let it sit for a while and then come back. Now our graduated cylinder is clamped in so as not to tip over. The reaction is still going. It's been going for about 10 minutes. The magnesium is disappearing and hydrogen gas is forming. Now while we're waiting, let's make a few other measurements here. We have to measure the atmospheric pressure. We're going to measure the atmospheric pressure with our gas pressure sensor. It has a small hole the air can go in, and it's connected to a LabQuest, and it reads the pressure for us, 29.39 inches of mercury. Let's add that to our data table. 29.39 inches of mercury. Next then, we need the temperature of the gas. Now, we can't put the thermometer inside of the graduated cylinder, but we can measure the temperature of the water and then go with the assumption that the gas is pretty much the same temperature as the water, which is 17.1 degrees. So let's add that to our data table. 17.1 degrees. To get Kelvin, we just add 273. That will give us 290.1 Kelvin. Remember, Kelvin doesn't have a degree symbol. All right. The last thing to do for data collection then is to wait for the gas to stop reacting. And it's still bubbling a little bit, so we're going to just let it go for a while, and then we'll come back to see what our final volume is. All right, it stopped reacting. It's been about an hour. So let's take a look at what our final volume is. Now it's upside down, so let's look at it like this. Looks like our final volume is 47.0 milliliters. Let's write that in our data table. 47.0 milliliters. Convert to liters. 0.0470. So that's our final volume. Now for these calculations, there are a few questions here that are related to topics that we're going to learn later in the year. So we're going to do some of this together. Number 1 says, copy down the balance chemical equation between magnesium and hydrochloric acid. All right, that was on the beginning there. Magnesium, and we write little s behind it, meaning a solid, reacts with hydrochloric acid, HCl. That's aqueous, meaning that it's dissolved in water. And it produces magnesium chloride, which is also dissolved in the water. That stays in the graduated cylinder. And then there's hydrogen gas, which is H2. We'll talk about why it's H2 a little bit later in the year. But that's your hydrogen gas. Now, to balance it so that there's the right number of atoms on both sides of the equation, we have to have the formulas written correct. So MgCl2 is the correct formula, and we would need a 2 in front of HCl, and then it is balanced. All right, we'll learn about that a little bit more later. What this means is that one atom of magnesium will react with 2 molecules of hydrogen chloride or hydrochloric acid, and it will produce 1 molecule or formula unit of magnesium chloride and 1 hydrogen molecule. All right, that's our balanced chemical equation. Now, question 2 says, how many moles of magnesium are reacted? Now, from our data that we had, we know that we reacted 0.06 grams of magnesium. That was the little chunk of magnesium. Now, from this periodic table, we have what's called the molar mass, 24.31. That means 24.31 grams for each mole of magnesium. We'll learn about this a little bit more later. But I could use that right here. I could write 24.31 grams of magnesium for each 1 mole of magnesium. Now, if I multiply this, 0.06 divided by, or times 1 divided by 24.31, that gives me 0.002 moles of magnesium. So that's how many moles of magnesium we used. A tiny amount of moles. Now, question 3 says, how many moles of hydrogen were produced? All right, this is a problem called stoichiometry, something that we'll learn about later in the year. But it will work like this. If I start with 0.002 moles of magnesium, then I multiply it times what's called the mole ratio, which is in the balanced equation. Moles of Mg is 1, because there's an implied 1 in front of Mg. And the moles of hydrogen gas is also a 1, because there's an implied 1 in front of the H2. So for every mole of hydrogen, or every mole of magnesium that I consume, then I'm going to make 1 mole of hydrogen gas. So in this case, I'm going to produce, or should produce, 0.002 moles of hydrogen gas. Now that is N in the equation PV equals nRT. So N is going to equal 0.002. These remaining questions are for you to do on your own. I'm going to give you this hint. To convert inches of mercury to kPa, I need to know that 29.9 inches of mercury is going to be equal to 101.3 kPa. That's your conversion factor. Number 5 is to rearrange using algebra, solving for R. Then you're going to get a value for the ideal gas constant. Number 6, calculate the value for R using your experimental data. Remember that R now is going to have units. We want it to have units of kPa, liters, over moles, over Kelvin. And then we can compare that to the theoretical value that you can see down below. Theoretical value for R. Then there's an extension question. Again, will be on your own. All right, good luck.